All right, so let's begin today's session. Good afternoon and assalamu alaikum, everyone. Allow me to welcome you to the Center of Water Informatics and Technology in the session of Models, Learning, and Sensing in Hydrology. Our panelists here include Dr. Abu Bakr, who runs the center. He's also an associate professor at the Electrical Engineering Department at LUMS. There is Dr. Javeria Ahmed. She's also associated with the center itself as a postdoc. And I'm Zara Lakdawala, who's also working together with the center from the Department of Mathematics at LUMS. Our speaker today is Dr. Carlos Rivera Villarius. I hope, Carlos, I've pronounced your name correctly. And a little introduction on him. He's done his MSc as a civil engineer in civil engineering from the University of Peru. He's done his master's, second master's, I believe, in water resources from Ben Gurion University in Israel. And he has a PhD in hydrology from the University of Potsdam in Germany. And he currently works at the Danish Hydraulic Institute as a product specialist and a product owner in VFlow. It's a software, and maybe Carlos can elaborate on this a little further in his talk. He's an expert in groundwater and unsaturated zone modeling, along with parameter estimation and uncertainty analysis, to name a few. And I'll open the floor to you, Carlos. Maybe you can take it on from there. Herewith, I welcome you again, and thank you for taking our time for this conversation here.
Yes, thank you, Sarah, for the nice introduction. And it's also a pleasure for me to be here in this technical presentation. So the topic of this presentation, it will try to give you an overview of what we have been working in the last years with our groundwater software tool called VFlow. We try to go a bit more beyond to the classical numerical modeling. So we will try to address and quantify what is the uncertainty of a numerical model for any specific prediction. For this, I have prepared, beside introduction, two examples. So one example will be related to a mining application. The second example is a geothermal project that we actually was part of one of my master students who just finished last week. Actually was the defense, and I'm happy to present these different results. So okay, so what is DHI? So I come from DHI, so this is the Danish Hydraulic Institute. So I'm particularly not based in Denmark, I'm based in Berlin in Germany. So DHI has a number of offices around the world, and our core is supporting sustainable development, so really in our DNA. So we have a significant, though deep domain knowledge in different water challenges. We have a number of technologies that I will show you later to cover different aspects of the water quality and water resources. So we develop software. We also provide advisory solutions, so consultancy, and we try to combine the best of these two worlds to help to achieve sustainable development objectives. So we have more than 50 years of dedicated research, so about 1,000 employees, 30 offices around the world. We have involved in projects in 150 countries, so our portfolio is consistent in public industry and also consulting companies. The technology stack of DHI goes through what we call the MIC family, the MIC simulation and modeling. So these are the core technology developed from the very beginning of DHI. And VFlow, the product that I'm going to discuss today with you, is part of this MIC technology. On top of that, we have developed different interfaces and business applications to interact with our simulators engines or mic operations, business applications. We also recently, or not recently, in the last years, we also elaborate data portals where users can store information, but also obtain easily information to build models. And we have a number of operational services as well. So we look the our integrated platform. So we move from what is groundwater, the topic of this presentation, with VFlow. So we have a MyPlus, what is everything related to surface water modeling, urban water, wastewater treatments and optimization of wastewater treatment plants with WES. We have an interface for operating and doing scenario analysis through multiple softwares with micro-operations. And we have an interface, a GUI for the different applications behind. Looking the whole water cycle, so the portfolio of DHI tries to cover every single piece of this water cycle, from urban water, rivers, channels, networks, integrated catchment hydrology, real catchment scale with MyShe, surface water, but also marine application with My21, with My3, integrated water resources management with MyHydroBasin. We also have some tools to support decision makers in the urban water sector called WaterNet Advisor, groundwater, VFlow, and wastewater West. Since a number of years, DHI is building applications in different aspects. I will just quickly show you a few things here. So we have applications for evaluating flood risk. In all of these applications, you do always have a numerical model, so a deterministic model doing something behind the scenes and trying to estimate certain scenario of probability that something happens, no? Like Plumcast, so this could be its utility to use or to determine oil spill in the ocean, or climate change adaptation, or vessel check. So that's quite also sophisticated. So it can optimize the positioning of the vessels in the different ports around the world, and saving minutes could save also several hundred thousand of euros for these different companies. Data portals. So we have information centers where modelers like you, users, could just come to these portals and download the information that is required from bathymetrics, meta-ocean, marine animal movement portals, and so on. So we are working even in more technology in these aspects. Operational service. We have different digital twins linked to our software technology. So one specifically for the topic of this presentation is groundwater. It's called MyMine, where we have in one single location a data store, so the user can store any information from the field, but at the same time could also store information linked to numerical models, so we can have everything in the same location. Models can be automatically updated every time that there is new measurements coming, and we can do some forecasting route from that scenario. DHI also invests quite a lot in the program what we call Academy by DHI. So we have a number of partnerships with universities, collaborative research. So we support a lot of students with licensing, but also supervising thesis work. We do workshops. We try to generate different user group meetings around our different softwares, because it is important for us to understand how they operate with the software, or what are the possible things that we can improve. Free webinar, self-paced courses. So if after presentation you would like to learn more about water modeling with VFlow, so you can just log in our website and for free get access to a number of different courses, modeling courses. Beside the training, so we are also offering technical support with our software and so on. But let's go to the topic of this presentation. So it's about VFlow. So VFlow maybe is new for some of you. So VFlow is a finite element simulator for flow, so groundwater flow, contaminant transport, so multi-species transport, kinetic reaction, geochemistry, groundwater age, and heat transport. So it's a software which is capable to operate under fully saturated or variable saturated conditions. So VFlow is not a new software. It exists since the late 70s. The software is, from the beginning on, was a finite element, and it was originally developed here in Germany. Still, so the major part of the development team is based in Berlin, in Germany, in my office. VFlow was acquired at some point by DHI, and from then it was really commercialized strongly in the international market. So our development schedule is twice a year we have development. So you can see the timelines here. We are quite active with the developments, and we try to actually do quite a lot of improvements in the software, not just from the graphical interface, but also from the way how the physical processes are being solved. So we just recently introduced an solver which is capable to handle GPU accelerations. We also have hydromechanical processes being coupled flow and mechanical processing in the software. So it's quite a lot of interest in DHI to improve not just the interface, but also the weights, how the software solve the physics. No. So VFlow is designed as an all-in-one solution. So we have one interface, so you learn one interface. You can operate with this interface for your flow simulation, mass transfer, and heat transfer. The software is designed that it will help you to save quite a lot of time and boost efficiency. Like if you do a simple model, you can just in a couple of minutes create a model. If you work with more complex data, so 3D data, geological data, you can interact with interfaces to import most of the standard file formats. We have some smart advanced meshing algorithms in 2D and 3D. We have also programming interface to speed up workflows. And because we believe that visualization is really it makes a good help to explain complex processes happening in groundwater. So we pay a lot of attention in visualization in VFlow. So from 2D, 3D visualization up to animations and virtual reality. So if you want to demonstrate and show your results to a non-academic community, so VFlow is quite helpful for that purpose. I will skip this one or just give it quite fast because I was already saying a few things. So the package is developed for solving finite element methods from simple to complex, or from a number of scales, or from baby dampers to regional models. So one project, one file control the whole setup, one single interface. And we support our users in the entire modeling workflow, from conceptualization, simulation, calibration, prediction. I should actually write here also uncertainty quantification here, so which is the direction that we will try to go here. So how is it now with most of the softwares available open source or academic or commercial software? So it's normally you start with a concept, so you build a mesh, put parameters, run your simulation. So this has been or is also the case of VFlow. The direction what we are going into the next year is to try to help the user to conceptualize all these problems at the very beginning. So now is if you realize that you want to change something in your concept, but you have already created a mesh and do the parameterization, so you basically need to go back to a number of steps, which is impractical and does not help us to understand and quantify the uncertainty. Let's say if I want to do evaluation, what is going to happen if my conceptual model is changing somehow, maybe rivers locations are different or material properties. So we are trying to build in VFlow in this year release and in the next ones too, a number of processes where the user can build the entire information, parameterize, and this meshing process is postponed at the very end. So the user will not need to redo a number of steps here. Uncertainty quantification. So that's the topic of today's webinar. And we start this already a number of years with an interface that we call FIPES. It's a VFlow interface for parameter estimation. This interface is available with the software and is being developed in the last years. So we did a significant upgrades the last months of this interface. So what you have in this interface is a number of methods to calibrate. So from the simple task to calibrate a numerical model, so to solve the so-called inverse problem. So this will be the most basic task that you can do here. So you have a number of observations, you have prepared your groundwater model, you plug everything together, and this interface will help you to minimize some function. Our objective function is called. But we also have a number of, let's call it advanced methods, where we can do Monte Carlo analysis or Pareto frog analysis, where the user could perturb certain information about the parameters, and we can understand what is the output of the model results of the model from that parameterization changes. You could imagine all this, it's a lot of numerical effort, a lot of number of runs to be behind the scenes. So there is a strong parallelization with FIPES. This parallelization can be locally, so if you have a number of cores in your machine or in the server, so if you can deploy externally these runs. But we have also been working in cloud support for the parallelization. So especially now we will have a software release by the end of May. We have really a one-click approach where from this interface you can deploy thousands of model runs in our cloud infrastructure. So especially for cases where you need to train the model with a high number of samples, so that will be really beneficial. So when we start this journey of uncertainty quantification and parameter estimation, we look what was available or what others were doing. From the groundwater perspective, PESO is a software developed by, so a number of years, so I guess now it's 25, 30 years. It's a software developed by John Doherty in Australia. Has this company called Watermark Numerical Computing, and we decided to work with PES or integrate PES into our VFlow work, because PES has the advantage of being a model independent parameter software, estimation software. It means that we have certain flexibility to modify as we want the solver, the engine, and we can still link it with PES. So PES basically does automatic calibration, and certainty quantification comes with a number of tools to carry out a number of applications of process. However, the major disadvantage of this interface is the fact that PES does not has a graphical interface. So especially if there are users who are working in a consulting industry, so they normally have a limited time to do some tasks. So learning a software with a graphical interface, scripting sometimes is not a good option for them. So we thought how we can facilitate this. So we build on top of that what I was presenting before, this FIPES graphical interface based on this. So the user will be running behind the scenes PES, and then and we will take advantage of this and then do entire processing for all the models. So here I put part of the different things that we can do. So from the calibration, or better say history matching, so you have a number of observations or measurements, or groundwater levels of flow, concentration, temperature, any kind of measurement that you have. it's possible to be imported in that interface, and then the inverse problem will be solved. So that's the basic configuration. So when we solve this inverse problem, where I will go later in the different equations, so we have a number of results, that a number of preliminary results. So we compute something, Jacobian matrix, where we can derive, for example, sensitivities of a model, of a parameter, linear uncertainties. We also do some Monte Carlo analysis and other stuff. So the way how these models are parameterized is also quite expensive. No, it's number of runs, but also number of parameters. So could be a highly parameterized model with 100,000 parameters. So we need the ways to identify or minimize the dimensionalities of the problem. And for this, so this tool comes equipped with several subspace regularization methods, so singular value decomposition and Tikhonov regularization, where the user can impose certain information to help to solve the inverse problem. So I put here a couple of examples about what are the typical outputs of this. So this is an example here. There is excavation. So we try to estimate how much is being seepages here. So this is a distribution. So normally the model is highly parameterized with conductivity values, with hydraulic conductivity. So what we try to do in this analysis here is to identify what are the locations which is really important to calibrate, or to even have more measurements, because they will affect directly the results. Or we could also come out with such a sensitivity maps, where we could have a map for a specific target observation of fusion prediction. So if I'm interested to estimate this location in a better way, so the software can tell me, okay, these are the most sensitive locations where we need more information, or we need to go to the field and take a measurements in order to minimize the uncertainty here. There are some methods where since we know the number of dimensions of the problem with all these singular value decompositions, and so we can draw such maps here, so where identifiability, where we can trace, okay, these are the locations based on the measurements that we have. So here the little flags, no, that we could really calibrate the parameters, no. So such a things is obviously valuable, and try to bring the bridge between something's really complex from the mathematical point of view, like a singular value decomposition, to the application. So at the end of the day, so the decision maker or the stakeholder would like to know, so where is actually important to have a model, where is actually important to calibrate. Other examples are Pareto from methods, where the user can test a couple of hypotheses. So what I could calibrate the methods, the model better, but I could maybe balance better my predictions, so we can come out with such a Pareto from the model results. On Monte Carlo based methods, so where you have a number of parameter realizations which could be derived from certain prior information, typically is a covariance matrix passed to establish this number of realizations. So FIPS can generate all these parameters, populate a number of models, and we can just deploy and run it. But before I move to this one, so what we notice here, so I mean, the Monte Carlo methods are really not new, so it's something that exists since a number of years. So what is the major, let's say, limitation of this technology is that the number of runs. So we always have a high number of runs, and it's always a limiting factor for the users or for the applications if they really want to understand and go beyond the typical model calibration or solving the inverse problem. So with that, so we knowing this problem, so we implemented recently we utilized a package, better said, which supports the iterative ensemble smoothing techniques for groundwater models. And this is the succession of what we have done before with PES. Is a package called PES++. This is developed by the United States Geological Survey. And it's a model independent package. So for VFlow, but there are also other softwares which utilize it. The package is really recently. It has two major key points. So we do in one single job a calibration, so a history matching, but we do also get some information to understand what is the uncertainty from the predictions. And all of this, even with the less number of model runs. So it sounds quite promising, and that's what we tested, and this is what I would like to show you in two examples. The next slices. Again, still it is an objective function which is minimized. So behind the scenes, so with what PES is doing is just solve this Gauss-Lembert-Mauer algorithm, which is quite common and famous for estimating the inverse problem, or for solving the inverse problem. So I will not go through each of these terms, so you can get my presentation if you want, because we don't have much time for this. So what it's doing is trying to rewrite or reformulate the GLM algorithm, so with the embedded iterative ensemble smoothing framework. And we follow this approach from Chen and Oliver 2013. So this is the method followed by PES++, where all the different terms of the standard GLM are now expressed in terms of ensembles. So we changed from a vector to a matrix to a grade matrix, where we have a number of ensembles times number of parameters. So we have a number of realizations, which is a user-defined information. We have now the observations, which were typically just simple vector defined. So it's come back here. This will be defined the different residual simulated values versus observed values. So now this becomes a matrix defined by the number of ensembles or observations. And what is also very different compared to the classical GLM methods here is that the most numerical expensive part of this is the calculation of the Jacobian matrix, which depends on the number of parameters and observations. If we go to a highly parameterized model, so we can learn more about parameters, but it takes a while to calculate because we have more parameters. So this approach derives the Jacobian matrix empirically, so which is cheaper numerically speaking, and it makes a certain independency of the maximum number of parameters. Of course, we cannot minimize so much the size of the matrix because could be also problematic. So we apply this in one of our projects. So really recently, it was a test case. So this model exists in a number of years. The model is a mining application. So it's a copper mine. So it's a numerical model. So this is the area of the numerical model. So I didn't write the dimension, but it's a number of kilometers, really a regional scale. The model was developed to contain all the different heterogeneities in the system. So we have here example of a cross section with conductivity distributions. So here is the mine, and the VFlow model. What it does, it simulates the typical mining plants, also excavation processes. So we have these red areas where the volume is being excavated. So VFlow is capable to remove these blocks. And what we do is we remove, so we open boundaries to generate seepages. And the model has been calibrated for a number of years. So we have one single model, which is representing the history of the measurements. But we thought, okay, we can do better than that. And we embed this model into this framework with PES++. So the model was heavy to run. So simplify, we extract a part of the model and set up a simple model, which can run quite fast in VFlow, so like half an hour. This model requires a parameterization. This parameterization uses a method called pilot points. So we have a number of points where conductivity in this case will be estimated in between the points. So we need to fill the entire model domain. So we do a 3D grading interpolation on the fly. And in total, we use for this model 146. So it's really not a big number of parameters. Observations there were quite a lot because there's a lot of transient recording of water levels. So, and we also estimate, or will not estimate, so we estimate what is the total discharge to the mine. So here you imagine you have a hole and the water level is here, so it's discharged into this hole. So we want to actually understand what is the uncertainty of this prediction, because this is the most relevant, since as the user want to know what will be the pump rate to maintain the mine dry. So we decided to go in a 150 ensemble, so it's kind of in the level of parameters, and just test the generation of ensembles following a Gaussian distribution with some values of standard deviation. And what you get is such a picture where this is a negative, so it's an outflow in cubic meters, so this is a volume being discharged. So it's a base model here, so this is the initial model, and we have a number of realizations. The nice thing from this picture is that you can clearly identify what is the worst scenario here. So we have a scenario where we have a significant increase of the dewatering volume. And this obviously is relevant for the user because it can help them to be prepared for such a case. Nicely, you can see here that the model, so what is all of these lines here are capable to calibrate the model, but they do differ a very different estimation of this dewatering volume. A second example, it goes really in a totally different direction. Is something really just put the day. Even so, last week was defended this master thesis. It's a student who was working with me the last 6 months. She developed a nice thermohydraulic numerical model with VFlow. So just to bring a bit of context of the modeling area. So the model is located here. So it's really a model which is enclosed in part of the city of Munich. So the model represents the so-called Bavarian morass basin. So it's a really famous geothermal reservoir in Europe. Is already utilized for a number of companies where they have extraction wells for geothermal applications for energy production and heating. Also, so that I will not go into the geology or structural geology, so I just put the image here. This is quite complex, the geology, so there is a lot of also uncertainty of the geological features. As a reference, so that's the model area. So the city of Munich is here. There was already existing model. The job of this student was to update the model in this polygon here. So there was a 3D seismic campaign, which ended up having a different interpretation of the structural geology, which is a problem in some case for the person who was doing the model before, because differs quite a lot. So it was a challenge to update the model. And that's why we thought, okay, there are a lot of unknowns parameters, so it makes sense to embed this numerical modeling in an uncertainty framework. So there is a number of steps here, so I will just go to the uncertainty part directly. So the model I was saying, there was already a numerical model. So this student was preparing a number of finite element models. So also the meshing part here was really challenging because the number of faults are really complex. So we use tetrahedral meshing for the reservoir. That's why there was a number of models, of course, final version, which were validated from the model, then we run a number of scenario analysis where we just move the location of future wells. So we know that the city of Munich in the next 20 years is going to move in the direction of CO2 neutral. So they want to do more geothermal applications. So they are planning a number of new wells. So we use the model to design the location of the wells. And then at the end, we took one scenario with uncertainty quantification. So these are some pictures of the model, different models. So this is the so-called original model without the updates or coarse final mesh. So you can see some clearly differences, which depends on discretization. Also validate the pressure, which is very important for this reservoir. No, so the pressure is equivalent in the different models. So saying that we come out, okay, the validation was succeed, so we can move forward from this numerical model, and then we end up with multiple scenarios. So these numbers are different boreholes, geothermal boreholes, and colors in blue are injection wells, in red are pumping wells. Sometimes the boreholes are coupled in two, so called doublets, or in three triplets. In some locations you pump out, in others you return the flow because you want to have the reservoir equilibrium in terms of pressure. What is also important is to evaluate if there is a thermal breakthrough. So if you are injecting back cold water, is this cold plume arriving on the production well, so the pumping well? If so, then it's a problem because you cannot be sustainable with the energy generation with this reservoir. So there was a number of scenarios here. The model, each scenario runs 48 years, so in the future, so until 2060. So just to look here, so you see this is a temperature distribution. This is the injection wells. We inject back always 50 degrees, so we track basically whether this purple plume move in the direction to the other black dots. If so, then it happens a thermal breakthrough, which is a problem. Also, the pressure has to be checked. And from this, do not go too much into the details. So we choose the best two scenarios, and we combine a so-called four scenario, which was used to do the uncertainty quantification. In this, so we took the model with VFlow, and then we parameterize the model. So we choose hydraulic conductivity, porosity, and thermal conductivity. So there are the three input parameters for such a geothermal applications. These parameters are populated in the model, in the 3D domain with the Krieg interpolation. So we use here a pilot point parameterization, again, the number of points in the domain, so 500 points in the domain. Each of these points has its own Gaussian distribution, which we know from some measurements. So we know some prior information of the model. And then we run a number of VFlow cases, no, just to give you a picture of the different pilot points. So each of these dots is a pilot point. So the background map is the conductivity in the reservoir. So it's a log transform distribution. So this is how it normally looks for one of the pilot points. So the conductivity could change several order of magnitude in the reservoir. So it's a lot of things to evaluate here. So using this framework, we came out with the following. So we have a number of measurements. We calibrate these measurements. So this, you see the error means square, root mean square error. So for all of them quite small, so it was really good, well calibrated. But at the same time, because we're running a number of ensembles, so we can understand what is the variability in the predictions due to all these different ensembles. So for example, this point, which gave me a measurement of 90, no? So although we have a lowest ring square error, so we can, it could vary from 90 to 80 Celsius degrees. So, but why is important that? Because we are planning to operate new systems, so we try to see identify what are the best or worst case scenarios. So here in this chart, what you see is 2 of the wells, of these 12 wells, we just did a cross section. We have the initial temperature, so before the well was operating, the predicted temperature, all of them in gray, the mean value of all of the predictions. The temperature goes down to 50 degrees because it's injection well. And then if you move several meters, 100 meters apart from injection well, you can see that the uncertainty here is quite large. It could just change a lot of Celsius degrees in this range here. So if we have a production well that is nearby, so it will be quite probable that there is a thermal breakthrough appears here. For other wells, this variability in the predictions is less. So for example, the well number 7 here, more to the south. So the, the variability is a couple of Celsius degrees. So this information is valuable because the decision maker or the stakeholders needs to understand. So it will be a 50, it will be a 60 degrees, or how much will be the variability if I operate these wells. I reached the end of my presentation, so we have quite a number of quite some time later to discuss. So I will not conclude quite specific, so I just want to, as a mere conclusion here, say that this iterative ensemble smoothing techniques is, well, it has a significant number of advantages compared to other methods. And the main one is that it's capable to reduce numerical effort. So we have been testing in real case scenarios or large models, though. So where we are capable to quantify uncertainty without really scaling significantly the number of model runs, which will be the case of a typical or classical Monte Carlo analysis. And secondly, nicely, the method can combine the two worlds, so the typical inverse problem with the GLM optimization or gradient-based methods, doing some model calibration or history matching. But at the same time, give us as an output uncertainty quantification, which is even more valuable for the end user. So with this slide, I would like to thank you for your attention, and I'm happy to answer any questions or comments if you have any.
Thank you, Dr. Carlos, for this presentation. We do have a few questions, so let's take those turn by turn. The first one is that Salman Khan was asking, what is the difference between VFlow and Mudflow?
Okay, so this question is quite common for me. Yeah, so these are totally different words. So VFlow is a finite element method, Mudflow is a finite difference method. So from that, it's quite different. So Mudflow is an engine, so developed by the United States Geological Survey. It's kind of updated once in a while with different releases. It doesn't have an open graphical interface, so the users will just take the engine and run in the console. There are a number of tools which can help you to operate with Mudflow engine. So VFlow differs because when we develop this in DHI, we take the full responsibility of both. So the numerics, and the graphical methods of the software. So that was give us certain flexibility and independence of release and update the software so often. The other major difference comes from the methods being solved. So finite difference and finite elements, so there are totally different approaches now. So this involves that also the discretization in VFlow. I don't know if I put this example of discretization here, but the discretization in VFlow is quite, you can say, flexible. It's quite is unstructured, could be triangular or tetrahedral based. So Mudflow, classical Mudflow, will be limited to quadrilateral meshes only, where sometimes is a problem because you need to simplify reality, especially if you do complex geological settings like these ones.
All right, thank you. So there's another question concerning the resolutions in terms of what is the maximum area that can be handled, that can be modeled by VFlow, and this in the same line, what is the minimum spatial resolution that can be used to model reliably?
Yes, so from the software itself, there is no a limit in terms of the size. It's mainly a limit in terms of the hardware that you have to solve. No, is if you let's say this reservoir here is several hundred square kilometers, so it's quite large. If you decided to go in a very fine discretization, so actually this was one of the tests of this student. So she was arriving at quite high numbers, so several million finite elements. And for the physics, so we solved flow and heat here equations. So it was quite a large problem for the today's typical hardware we have. So I don't know, 12 CPUs or 24 CPUs. It took a number of days to run. So it's that's one needs to take into consideration. So what hardware do I have to be able to couple to solve this in VFlow? From the software itself, there is no really a limitation in terms of the size. We can do box models. We can go to really small scales. I was giving the example of fluids in pampers or in baby diapers. So it's another scale. There is a company doing a number of VFlow simulations for understanding how effective are the absorption of these fluids in this small scale. But we also have number of VFlow examples, the large regional scale. I hope this answered the question.
Yeah, and I think, I mean, on this line of conversation, one could probably even mention a comment here in terms of mesh and models. VFlow can handle both sort of adaptive, fine, and coarse scales as well.
Yes.
Yeah. Okay. So there's Carlos, a lot of questions are coming in, so I'll probably take them line by line. Then there's another question which says that after calibration and validation of the VFlow model, how could you consider the uncertainty in the model for future projections?
Okay, yeah, that's a very good question. Thanks. I'm just trying to look the question. Hope I have fully written here. Yeah, so what we do is maybe not, maybe you can here. So if you want to if you have a prediction or you want to predict something, if you want to understand the uncertainty of something that you would like to predict with these numerical models. So what it's typically doing, so these methods here, so they minimize a function, the objective function. This is no more than a square weighted residuals. Weighted residuals is the weights are the key part. So if you have predictions, so what we typically models do is they define the location of the prediction. So like in this example was, we have a boundary condition. So we would like to get the flow rate through this boundary condition. This will be my prediction. So we embed this information as an observation. So we have a vector of observations. There will be one piece of the vector, which is a prediction. And this prediction has a weight of 0, so it will not influence the minimization of the objective function, because the objective function will be calibrated for non-zero weighted observations. But the software has the capabilities that at the same time, although it's not influencing the objective function, I still capable to monitor what is happening with this zero weighted prediction. So like this, I can put as many points or monitoring points as I want here. And VFlow, VPS does the calibration job and keep an eye on those predictions, and we'll end up at the end of the day with a list of predictions for all these different observations.
All right, thank you. So there's another question concerning VFlow. Does VFlow have the capability of directly assimilating data? For example, ensemble Kalman filtering if we have groundwater modeling station data?
Yes, we do not at the minute, so let's say in the commercial version of the software, but we are working in methods that could support us on that task. So actually DHI, other softwares of DHI, they do have a package of data simulation. So we use for surface water modeling, so packages of data simulation, applying ensemble Kalman filtering as well. So it's for us a matter of transferring the knowledge from one software to the another toolbox. What do we have sometimes in projects where it come these questions? So we develop kind of small toolbox with Python scripts or others, no, which are really just applied to the project. So we are trying now to see all these different toolbox that we have around different projects and see how we can mix it in one, and hopefully in the near future have one standard package.
I mean, this is something that even I can vouch for because I myself have worked on certain interfaces that link VFlow with your own implementations. And there is a way that you can tweak into different places of the modeling part, of the parameter setting part, of the numerical parts, if you want to tune it for your own purposes based on whatever data that's coming in. So thank you, Carlos. Another question, we're kind of running out of time. So maybe I'll take another 2 questions here. So there's one which asks, you used Kriging for the spatial interpolation in the model that you showed. And have you considered any other methods? Do you plan to implement something like random fields theory or something similar?
Okay, yeah. So we use here all these cases Kriging, so 3D Kriging. Why? Because it's, I mean, so Kriging is actually popular. It has advantages or disadvantages, no? So in VFlow, we have a number of interpolations, so radial-based functions. So we have a Kim interpolation. So we recently also implement something to area weighted projection that is no more than optimization of values. So if you have some cumulative, let's say, precipitation that you know in the catchment should come a number of millimeters a year. So if you interpolate, you might overshoot or undershoot that. So we have a variation of interpolation method where we can create certain rules to minimize or maintain these conservative amounts into the system. About what was them random field methods? So no really. So there are a number of tools from others, so from PES, which are capable to generate random fields. So we use some of these tools as well, but the user needs to really know a little bit more about these technologies of the tool to be implemented with VFlow. The nice thing with VFlow is that we have a really extensive open programming interface. So nowadays, everyone is we see from universities and consultants working with VFlow, everyone is working with the VFlow Python interface because Python is an easy language to learn, quite simple. You get a lot of geostatistical packages. So you are able to prepare all these parametrizations in the ways as you want and just inject all this information at the end before the model runs.
All right, thank you. I think a related question here is if we can use GRACE and GRACE FO data as an input to VFlow in order to have groundwater anomalies for any specific regions.
Okay, I need to really remember what is GRACE, so maybe can you expand the question?
So from what I know, GRACE is one of the satellite that was sent out, and it gathers a lot of data based on water, climate, water height, depth, blah blah blah. And this is one of the satellites that I think was with a combined project with Potsdam as well. Yes, that.
Yes. Okay. Yeah. So there is no direct link. So you can say just simply import the raster data coming from the satellites into VFlow. But what VFlow requires, I mean, is in terms of weather data, you require precipitations or outflows, evapotranspiration, evaporation. If you could, with post-process or pre-process actually this data from GRACE, then VFlow will be able to read most of the file formats that you can pass. So if you, I don't know, have text files, so we can just read the text files and use this input of precipitation to define the boundary condition. There are also satellite data, I forgot the name, one product to estimate global soil moisture. So this is also one of the things that I have seen in projects, not from us, but other companies where they start with the saturation of the soil from satellite data. Example cases are farming, so optimization of farms for irrigation. So they come out with some initial distribution of saturation coming from satellite. They put it in the model and then run with VFlow. But yeah, so there is no direct import from the satellites into VFlow. It has to be prepared by the user.
So would that mean that this would be a little bit of transfer of input formats in which you import data from? All right.
Yes. So yeah.
So I hope this answers most of the questions that the audience had. We have not too many more questions to go with. In case someone from the panel has a question, comment, please go ahead.
So I think I asked my question, and it was basically about data assimilation, and this later comment about this incorporation of satellite data. I think that points towards these similar concerns that if you have these models, which you can run for n number of steps, and then you can later marry them with data. But if you have the capability to assimilate data step by step, like on a very fine scale, that actually gives a lot of flexibility and a lot of power, so to speak. And as Zara was just testifying that this is really possible, so that's really intriguing. So I think maybe at some point I would like to talk to Zara about how we can learn some of that.
Yes, just looking now. Just let me share my screen again. So in DHI we are really even we have a specific department to operate remote sensing data. So we have data, I mean the names of the department chains. So we have what we call DHI grass. So that's so these guys here are really experts on interpreting remote sensing data. So they have a number of tools, so from artificial intelligence to simple processing, where you can get solutions for takes a while with the connection here. Solutions from soil moisture to so I'm trying to see here surface water monitoring using remote sensing, so that we can, using our algorithms, we can easily identify surface water bodies, urban mappings or floodings, water quality, so a number of products. Also, there was the latest one that I know is the soil motion, deep learning here. Yeah. So crop mapping inventory. So this is something that we are working quite a lot in DHI because there's a lot of interest. We have models which are capable to do the water balance at the field of the catchment scale. So if you can embed this information, remote sensing, modeling, do some predictions, so that is something that we are currently working on. So crop water monitoring. So that's, so that's we have a department working specifically in that. I'm pretty sure these guys also have some already implemented data simulation tools in their their software solutions.
All right, thank you so much, Carlos. This was quite interesting and informative. I think, just to stress upon the needs of the day as well, climate change is real. We're all feeling it in one way or the other. And predictions, modeling, simulations, and the ability to learn and react intelligently has become sort of the need of the day. Rather than a choice. And I'm glad we were here to discuss VFlow and interfaces like FEPest and so on, that give us sort of tools to actually do these kinds of predictions in a scientific way for intelligent decision making. Once again, I'd like to really thank you for your talk. And if you have some time, please stay on and we'd take up the questions and answers for a casual discussion in a closed panelist form.
Yeah, sure, I will stay. Thank you for the
Thank you.
invitation.